When the deforming force is applied to an object, the object deforms. In order to bring the object back to the original shape and size, there will be an opposing force generated inside the object. So what is stress? It is the measure of restoring force generated per unit area. Stress has a unit of force per unit area and is denoted by the Greek letter sigma. In general, the stress sigma acting on a plane surface may be uniform throughout the area, or may vary in intensity from one point to another. So this is the segment of the bar before loading. So this is an example. So this is the segment of the bar after loading. Notice the stresses acting on a cross-section MN, which are uniformly distributed over the area. Then the resultant of those stresses must be equal to the magnitude of the stress times the cross-sectional area of the bar. That is, P is equals to sigma times the area. So this is that. So as you follow the equation, this equation gives the intensity of uniform stress in an axially loaded prismatic bar of arbitrary cross-sectional shape. When the bar is stretched by the force P, the stresses are tensile stresses. If the forces are reversed in direction causing the bar to be compressed, we obtain compressive forces. So this is the sample problem. Diameter D, 2.0 inches, and the load P has a magnitude of 6 kps. Then the strength of the bar is, you follow the formula, and the 1.91 KSI or 1910 PSI. Next, we go to strain. So strain is the elongation of a segment equal to its length divided by the total length L and multiplied by the total elongation. Therefore, a unit of length of the bar will have an elongation equal to 1 over L times theta. In general, this quantity is called the elongation per unit length or strain, and is denoted by the Greek letter epsilon. We see that strain is given by the equation. So this is the equation. Then we have another sample program. Consider a steel bar having a length L equal to 2.0 meter. When heavily loaded in tension, this bar might elongate by 1.4 millimeter, which means that strain is So this is the computation, and this is the final answer. Next we go to stress-strain diagram. The first material we will discuss is structural steel, also known as mild steel or low-carbon steel. Structural steel is one of the most widely used metals and is found in buildings, bridges, vehicles, and many other types of construction. So we will show a stress-strain diagram. The diagram begins with a straight line from the origin O to point A, which means that the relationship between stress and strain in this initial region is not only linear but proportional. So see, this is the linear region. It is also proportional. Beyond point A, the proportionality between stress and strain no longer exists. Hence, the stress at A is called the proportional limit. So this is the proportional limit. For low carbon steels, this limit is the range to 30 to 50 ksi, 210 to 350 MPa. High strength steels can have proportional limits of more than 80 ksi or 550 MPa. The slope of the straight line from O to A is called the modulus of elasticity. So this from O to A, we call that the modulus of elasticity. With an increase in strength beyond the proportional limit, the strain begins to increase more rapidly for each increment in stress. Consequently, the stress-strain curve has smaller and smaller slope until at point B, the curve becomes horizontal. So, point B. So at point B, this is the point B becomes horizontal to C. Beginning at this point, considerable elongation of the test specimen occurs with no noticeable increase in the tensile force from B to C. This phenomenon is known as yielding of material, and B is called the yield point. So this is the yield point. This one is the yield point. The corresponding stress is known as the yield stress of the steel. In the region from B to C, the material becomes perfectly elastic. So this is the region from B to C, and it becomes perfectly elastic. The elongation of a mild-scale specimen in the perfectly plastic region is typically 10 to 15 times the elongation that occurs in the linear region. After undergoing the large strains that occur during yielding in the region BC, the steel begins to strain harden. Begins to strain harden. During strain hardening, the material undergoes changes in crystalline structure, resulting in increased resistance of the material to further deformation. Elongation of the test specimen in this region requires an increase in the tensile load, and therefore the stress-strain diagram has a positive slope from C to D. The load eventually reaches its maximum value, and the corresponding stress at point D is called the ultimate stress. This is the ultimate stress at D. When a test specimen is stretched, lateral contraction occurs, as previously mentioned. The resulting decrease in cross-sectional area is too small to have a noticeable effect in the calculated values of the stress after the point C. So if we further go, it will now introduce necking. When a test specimen is stretched, lateral contraction occurs, as this resulting decrease in cross-sectional area is too small to have a noticeable effect on the calculated values of the stress up to point C. In the vicinity of the ultimate stress, the reduction in area of the bar becomes clearly visible and pronounced necking the bar occurs. So another one is D because of the necking process, because ultimately the cross-sectional area is decreased. So actually the the strain increases. So this is the sample problem number 2. This is for the stress strain diagram for the typical structure steel in tension. And this is sample problem number 2.1. This is now the stress strain diagram for aluminum alloy. So what is Poisson's ratio? The lateral strain E prime at any point in a bar is proportional to the axial strain E at that some point if the material is linearly elastic. The ratio of these strains is property of the material known as Poisson's ratio. This dimensionless ratio, usually denoted by the Greek letter V, can be expressed by the equation V is equals to lateral strain over axial strain times negative. When Poisson's ratio for a material is known, we can obtain the lateral strain from the axial strains as follows. Hi, my name is Jose. So this is the sample problem. Thank you for asking me about it. So I believe you have an issue that you cannot connect to the video. This is the computation. First is the answer for letter A, the answer for letter B, the answer for letter C, and letter D. Thank you.